nanohub.org.
Dr. Majumdar, this is his third talk in about 14 hours or something like that. So he's setting the endurance record. But just to reiterate some of the things I talked about yesterday, I think we all know now he's the first director of ARPA-E, and before that he rose through the ranks and became a distinguished professor at Berkeley. He's been elected to the National Academy of Engineering, among many other awards throughout the years. And certainly he's already inspired us with his talks so far. Today, in the tradition of the Hawkins series, we have a more specific heat transfer focused talk that is given to more specialists in the field and other people who are interested in the field of heat transfer. And so this is a kind of a special way for us to get into some of the nitty-gritties of the technical details, so that's always fun. So with that, I give you again.
Great. Thanks, Tim. Thank you very much. You know, I was invited to give the Reynolds lecture at Stanford, and it's similar to the Hawkins lecture out here. And my assistant, by mistake, sent out. I had prepared an abstract about heat transfer and all that. But my assistant, by mistake, sent out the wrong abstract, sent out the more general talk that I gave yesterday. And I called Fritz Prince, who's the department head out there, and said that, I think the wrong abstract got sent. Do you want me to give the heat transfer talk? Because I think Reynolds, Bill Reynolds and all the fluid mechanics heat transfer. He said, no. People want to hear about your ARPA-E stuff. So I said, okay, there goes my scientific career. It's going downhill now. But I'm so glad you wanted to hear about what I do on my nights and weekends. I, still have my research group, unofficial, that's still graduating. We actually, frankly, published more papers this year than last year. But we have several in the review. So this is something we are still, I'm going to talk about things that we're still doing in the lab. And actually it's getting really exciting right now. And again, this is nights and weekends and Skype and WebEx stuff. But some of it is slightly older stuff, and you might recognize some of that. So, this is a famous quote. There are at least two reasons to give a talk. Either the material is so new that no one has heard of it, or it's so old that people have forgotten it. And I'll try the risky option of doing both. So some of it, I think it's important to sort of look at old problems with new tools, because old problems generally, many times don't go away. And I'll briefly touch upon that, and then I'll go into something which I think we're trying to penetrate a topic which is, it's turned out to be a science problem, but it really came from an engineering side. But if you can change the science, then we can go back to engineering. So again, you guys have seen this chart before. This is the Sankey diagram for the energy supply and demand. I just want to point out a different aspect: heat. Electricity is generated by heat today, and I don't think that's going to change in the near future. It might change long term, but not in the near future. At least not in this century. It's not going to change. Unlikely. Heating is about 40 to 50% of buildings. It is generally a very large fraction of industrial energy, because that's mostly petrochemicals. Cement, steel, paper, glass, these are all heat-based. And of course, transportation today is mostly engine. And, and it's not going to change. We hope it's going to change the electrified way, but it's not going to change anytime in the next decade at least. Engines are going to be there. Combustion will be around for a while at least this century. So given that about 90% of the energy landscape is heat, one should, at least in an academic environment, ask the question, okay, what are the limits? And there are many limits. Limits of phase change, limits of radiation, limits of conduction, convection, etc. I'm going to talk about just a few of them. One is boiling, heat transfer. This is an old problem. And the question is, can we throw some new tools at it? And I'll just one chart on this, and I'll switch to other things. This is the well-known boiling curve. You have nucleate onset of nucleate boiling. Then you've got nucleate boiling out here. It reaches a critical heat flux and jumps to film boiling out here. And and the critical heat flux is a big deal. And many of the people out here in Purdue have looked at this very closely. And it's about, for water, so it's about 100 watts per centimeter squared. And that has remained. I mean, you can increase it to about 200 or so. That's hard. But it has remained a practical limit. But it is not a physical limit. So you ask the question, what is the physical limit? The physical limit is when you have liquid and you have vapor, which is coming out, and the vapor moves at the speed of sound. And if you have the speed of sound, that is, you can't move things faster unless you have compressible flows and shock waves and all that. But for most practical purposes, let's say you got enough of a phase change that the velocity of these molecules of speed of sound. If you do the numbers, the density of the vapor, velocity of sound, HFG, you get about 10 raised to 5 watts per centimeter squared. We are a factor of 1,000 away from from the limit in the critical heat flux. The other aspect is this conductance, is this line out here. Can we move it sharper and sharper? I won't spend too much time on that. We have actually a boiling group in my group right now. They're looking at how to change this. How do we increase this number and approaching that number out here? It is really hard because there are length scales in this problem, hydrodynamic instabilities, length scales. There are other aspects of surface tension, surface chemistry that needs to be looked at. And we have gotten it up to like 600 watts per centimeter squared, but one really needs to dig deep into the science of instabilities and many other things and see if you can manipulate those length scales in some way. And as I said, by manipulating, we have up to about 500, 600 watts per centimeter squared with some microstructuring. You don't need nanostructuring for this. You don't need, we found that we don't need nano. We tried nano, didn't work. Then we went to micro, and you can actually start controlling things in the critical heat flux. And this conductance is typically around 3 to 5 watts per centimeter squared per Kelvin. We're trying to push it by an order of magnitude higher and see if you can push it even higher. And so these are the kinds of things, because this is relevant not just for pool boiling, it's relevant in heat pipes and many other devices, engineering devices. That is, if you could increase the limit, you can actually do a lot of interesting things. I mentioned this very briefly yesterday. Let me just go over it again on air conditioning systems, which is really important for building energy consumption, etc. And there's a systems aspect to it even in a building, because most of it are centralized chillers today. And even if 1 or 2 people are in the whole building, you got to run the chiller. And that's just inefficient. If you can do on-demand cooling as a system, you can actually do really well. The most efficient air conditioner is the one that is turned off. And so how to turn things off in a system level is really important. But as a device, there are, this is the ambient, as I mentioned yesterday, this is the indoor environment. And there are 2 loads. One is a sensible load, one is a latent heat load. The latent heat load, if you ask for the minimum energy required to remove moisture, it is the free energy of mixing. And that work, that is, W sub L can be obtained from from some heat in a reversible engine, and that's out here. And for the sensible heat, you need some refrigeration. And if these are reversible engines again, that is the minimum work that you need. And you can then go through this and you ask the question, what is the primary energy use? Not the secondary energy, but the primary energy use, which really is the carbon emissions or whatever you may think of. What is the limit? And again, how far are we from the limits? We think that we are about a factor of 10 away from theoretical limits. And at theoretical limit, you don't get any work, or the rate of work is really, rate of cooling is 0, because it is almost quasi-equilibrium. So there is an optimal somewhere in terms of cost, in terms of performance, but we thought that this is a target that one could go after and still be at cost, and in fact reduce the cost somehow. So this is a limit that is there, and I think there are many, many other limits, both system level limits and devices limit that can be developed. And I think it's really important to go through that exercise of doing system level limits and process and scientific limits, and to find out how far are we from these limits, so that at least we can, come up with a direction of R&D. Again, I mentioned this. This has nothing to do with limits, but has to do with the impact of the hydrofluorocarbons that we use in our air conditioning systems. And the most of the growth of these air conditioning systems or refrigeration systems will be in the developing economies. It's not here in the United States. And if that growth is going, and there is leakage in all these air conditioners, this HCFC impact of that on greenhouse effect is predicted to be about 25% that of CO2, because the global warming potential of these is about 3,000 that of CO2. And so this is a big deal. So are there other methods of doing cooling? And there are many other methods. You can use CO2 as a refrigerant. And in fact, we funded some projects in ARPA-E which have not just CO2, but CO2 in a very novel way, in using ionic liquids as a fluid, as a working fluid. To do that, magnetocaloric. Again, this is an interplay between entropy and enthalpy. Magnetocaloric, magnetic dipoles that can be aligned with a magnetic field, and you use the entropy to grab energy and become disordered. Thermoacoustic, thermoelectric. And there are many others as well. You can use magnetic dipoles, you can use electric dipoles to do refrigeration. At the end of the day, it's entropy and how disordered they are, and how you can use that entropy to grab energy, just like you do in evaporation. So I'm going to focus on thermoelectrics, because that's what my group has been doing, and I'll dig deeper into this. So what is this is a heat engine. It could be used as an engine refrigerator. You get semiconductors and p-n junctions, and you can use that, as I said, as a refrigerator or an engine. The key parameter out here is Seebeck coefficient. One of the key parameters, I would say, is the voltage that you get as a temperature difference across a material. But the performance of that depends on this parameter called ZT, which is S squared sigma T over K. Sigma is electrical conductivity, temperature, thermal conductivity in the denominator. And we want this parameter to be high, because the percent of Carnot that you can get is monotonic function of ZT. And today's bismuth telluride is the exotic semiconductor that is used, and that's at 1, and you get about 20% of Carnot, roughly. And what you really want to be is somewhere out here, ZT, system ZT higher than 2, material ZT preferably higher than 3. And one would think that it's easy to do, because each of these parameters can be manipulated by orders of magnitude, but put them together and it's really, really hard. Here's why. If you look at the carrier concentration in a semiconductor or a metal, as you increase the carrier concentration, your thermal power goes down. I'll get into why. Electrical conductivity goes up, and there's a peak. The maximum is at about a degenerate semiconductor, S squared sigma. And the question is, how high can this go? Or is there a physical limit? I don't think anyone has proven that there is a physical limit for this yet. And in the thermal conductivity, there's an electronic contribution, and there's a lattice contribution. And in the degenerate semiconductor, it's somewhere out here. The electronic contribution is a little bit there, but mostly lattice contribution. And you really want to reduce the lattice contribution so that this denominator in ZT goes down. And so I'll come to how one would do that. But this interplay between sigma K, they're not totally independent. I call this the Bermuda Triangle of thermoelectrics. A lot of people have gotten into it and haven't gotten out, including me and a few of my colleagues. It is a very intriguing problem, one of the hardest problems in materials design and material science and engineering. And We're hoping for a miracle or some discoveries, but it hasn't happened yet. And for the last 50 years, people have been trying this. So let me give you a little bit of the history. I'll come to the history. Here's why those interdependence come in. You ask the question, where does entropy come into the play out here? What is entropy out here? Well, entropy is the thermal power. Because when you go from a semiconductor to, let's say you go from a metal to a semiconductor, you expand your k-space for the electrons. And it is that degeneracy in the k-space that gives you the entropy. So it's like evaporation. Evaporation, you increase the k-space of the molecules from being bound to free. Well, the same thing happens when you go over a barrier and you essentially evaporate the hot electrons. And so that's the question is, can we manipulate k-space for the electrons? And so here is why there's interdependencies problem out here. This is, let's say you have a metal and a semiconductor. With a semiconductor, degenerate semiconductor, your Fermi level, your chemical potential is out here. For a metal, is deep down there. And you ask the question, where is what contributes to electrical conductivity and thermal power? The electrical conductivity for a semiconductor is low because you don't have enough carriers. This is the density of states out here. You don't have enough electrons. So electrical conductivity is low. For a metal, electrical conductivity is high. But the slope of the density, which gives you, if you heat up something, is there enough K space to accommodate, which is your density? You have much more of this slope, so the thermal power is much higher out here than out there. And thermal power is essentially the asymmetry of this distribution of electrons around the chemical potential. Okay? Because if it's highly asymmetric, when you heat it, you have larger K space to go. And you got larger change in entropy. But if it's symmetric, then you have very low. You don't have much change in entropy. That's really the fundamental, of thermodynamics of these electronic systems. And so when you have a semiconductor, you have low number of electrons, but you have large asymmetry. When you have a metal, you got large number of electrons, but you don't have symmetry. You don't have asymmetry. So that's the problem, the fundamental problem. And not too many people, and there are few, examples where this does not work, where you can change S and sigma in the same direction, but most systems, electronic systems, you cannot. There are cases where you can, and I won't talk about that right now, but maybe Q&A later on. And so how do you change, how do you change the S and sigma? Well, if you have a low effective mass system and a high effective mass system, the one with high effective mass generally has a high thermal power because you have a larger slope in the density of states. If you increase the energy a little bit by thermally exciting, you get more space, K space to occupy in a high effective mass system. So you really want a high effective mass semiconductor. Okay, so that's one. You want a degenerate semiconductor because you want enough electrons, enough carriers. But if you can get multi-band transport in these semiconductors, because one band, if you can get degeneracy, like in silicon, conduction band, you got 6 valleys. Okay, so if you can get that, that's great, because you got now more electrons. But somehow, if you can get these bands to be a little bit offset in energy, which in some semiconductors like bismuth telluride you go a little bit energy, you get interband scattering, and suddenly your thermal power goes up, immensely. So that's the kind of band gap engineering that needs to be done, or band engineering, actually, not gap, just band engineering that needs to be done in semiconductors, which is where the direction ought to be. And it's sort of going there. So how does one increase I squared sigma? Well, this was a proposal by Millie Dresselhaus and her team, is to go quantum structure, because you can then manipulate this density of states. And it is very attractive to do that. But it turns out that if you do go into 0-dimensional, 1-dimensional, or 2-dimensional, and you can manipulate this slope, the S, but you actually go down in carriers. So you don't actually win in many of the cases. But it's worth pursuing nanostructured electronics. The other one was, Alicia Kuris, was that if you have a metal and put a little bit of a barrier out here, you can create a symmetric distribution of the electrons to an asymmetric one artificially. And thereby you can essentially get the hot electrons to evaporate. This is like evaporation of like a liquid to a vapor. and get high values of S. And if you can manipulate it, you can still retain the number of electrons by manipulating this barrier height, and thereby you can get high S squared sigma. This has actually worked, and I'll show you an example of that. So that was the, so this is the history of ZT at room temperature as a function of year. Bismuth telluride was discovered in 1955, a lot of excitement. Then, it went from about 0.6 to about 0.8, and a lot of people got excited. Then for about 50 years, nothing really happened in this, and people were trying. A lot of people, as I said, this was a Bermuda Triangle for not just for us, for a lot of other people who've gotten out of it, got into other fields because they just couldn't change this ballgame. And Millie Dresselhaus's work showed that maybe nanostructures has a way. And what they did was, they said that the S squared, the power factor, the numerator of ZT could be improved, and thereby you get in. And people started making nanostructures. And yes, these were the nanostructures that were made. This is Rama Venkata Subramaniam's group, Ted Harman's group. This turned out to be actually not correct later on. But nevertheless, they showed that you can get to higher ZTs. This is Kanadzides' group at that time, Michigan State. And they showed you can actually beat this one value, one. There's no physical reason why it has to be one. There is no physical limit for this. Okay? It could be infinite, in which case you'll get Carnot. Unlikely, but it could. There's no physical limit for this. So they saw this and said, okay, nanostructures does increase, just like Dresselhaus predicted, nanostructures does increase your ZT. But what they found was instead of increasing the S squared sigma, which was the prediction, the electronic side, it increased ZT because of a reduction of thermal conductivity. And in all these cases, except for one, in all of these cases, the thermal conductivity went down. It had nothing to do with the electronics. In fact, in some cases, the power factor went down. But the thermal conductivity went down even further. So it turned out to be a heat conduction problem. Eventually, that was the outcome of this. So then he said, okay, why does heat conduction go down without affecting the power factor? And that was sort of the puzzle. So we said, okay, this is, if we can get to ZT of 3, this is a big engineering application. Let's get into it and see if you can understand this. So let me go down to heat conduction. This is, many of you know this, Fourier law of heat conduction is taught at undergraduate level. This heat conduction K comes from Brownian motion, essentially of energy carriers. And this motion has this is what we call diffusion. It has a characteristic length scale, a mean free path, which is sort of the average distance a carrier goes before it scatters. It has a speed of propagation, and it has, these carriers have a capacity to grab energy, thermal energy. So if you put that all together, this becomes 1/3 CVL, and he's heat capacity, the group velocity, and L. This is a very, sort of the first level, of peeling the onion from Fourier law. This is the next level of 1/3 CVL. If you peel it even further, you get to, Boltzmann transport equation. And this CVL can be broken up as a function of energy carriers because many of these energy carriers are not at the same energy level. They're different energy levels. So you have to, this is simplistic. You can go down even further. So this is, people have known this for a while. You can derive Fourier law and everything from Boltzmann transport equation. But at the fundamental level, what is often lost in that analysis of Fourier and Boltzmann is that these are wave propagation problems. This is a wave mechanics problem. So how is heat conducted on the lattice side? Well, you have atoms with springs, and if you jiggle this, you get a wave that is propagating, and these waves, just like any other waves, will scatter from the boundaries, scatter from defects in the material, or in this case, these springs are a little nonlinear. So you have the equivalent of nonlinear optics, where the springs, when you stretch them, the spring constant changes. So if another phonon comes, you can actually scatter each other. So that's phonon-phonon scattering. And that basically controls your mean free path. These combination of these control your mean free path. But at the end of the day, it is a wave. It is an acoustic wave at very high frequencies. And these, when they move around scattered, they produce diffusion. But just like in radiation, you have the equation of radiative transfer, which is a particle transport, approach to radiative transfer. But there is a spectral part to it. The same thing out here. There's a spectral analogy, which is if you go back to the physics of phonons, it is almost the same as photons. So there is a blackbody radiation curve. There's Wien's displacement law, and everything else is almost the same, with some subtle differences. But it is a blackbody radiation. As you increase your temperature, your max for both the wavelength and the frequencies will be increasing. And W max, this Wien displacement law, is given as this out here, and lambda max T is, that's Wien's displacement law. C is the speed of propagation. For photons, it is speed of light. But for phonons, it is the speed of sound, or speed of the wave packet that is moving. Now, of course, this is much smaller for sound than in light, and thereby lambda max T at room temperature for photons is about, at room temperature lambda max is about 10 microns, but because the speed of sound is few orders of magnitude lower, at room temperature lambda max for phonons is in the nanometer range. So this is the speed of, these are the differences in speed typically. So lambda max, instead of infrared range, which is 10 micron, now comes in the nanometer range for phonons. And so that's a difference. So you want to manipulate heat conduction, you got to go down to the, if you want to manipulate spectrally, you got to go down to the nanometer range. So that's really where it comes up. So what are the lower limits of thermal conductivity? How do you reduce K sub L? Well, you could reduce the group velocity, which is by group velocity is given as a square root of the spring constant divided by mass. And this is just like, this is classical mechanics problem. And so you can increase the mass by going to heavy elements, which is, lower down in the periodic table. So silicon is not the best semiconductor for this, presumably. And you can go to weaker bonds. So make softer material, van der Waals bonds or something like that, which will reduce your speed of propagation and thereby reduce the thermal conductivity. So it so happens that you go down the periodic table, in the semiconductor range at least, you get weaker bonds also. So, when you go down the periodic table, it works both ways. And thereby your group velocities reduce. Or you reduce the mean free path. Okay, so this is what people have used in the past. That is, you just take heavy metal semiconductors. And there you're okay then, because your lattice conductivity goes down. Or reduce the mean free path. The question is, how far can you reduce that? And can you do both? Or is this the best option that we have? So we started questioning this, and not just us, many people around in the scientific community started questioning all this. So how can you reduce mean free path? Well, since the 50s, at least in the thermoelectric field, since the 50s, people said, let's just put defects in there. You anyway need to dope these semiconductors. Why don't we make them alloys? Because if you put alloys, they start scattering the phonons, just like any defect would scatter phonons, or particles would scatter photons, they would scatter. And you get somewhere on the order of about 10 watts per meter Kelvin at room temperature by alloying a semiconductor. And as I said, if you want to control the band gap and the band structure, you need to alloy it anyway for the electronic side. You get a benefit, you get a benefit out of this, and you get low phonon thermal conductivity as well. The other limit is you make it amorphous. Okay, and if you make it amorphous, then your mean free path is on the order of a few angstroms, and because there is no crystalline order in this, and things will scatter, and you get a thermal conductivity on the order of 1 watt per meter Kelvin, order of magnitude lower, and you can predict that very easily. This is your typical heat capacity, which is Dulong-Petit limit in solids. This is a typical solid speed of propagation, speed of sound, and 3 angstroms. We just pick that, and you get 1 watt per meter Kelvin. This is not rocket science, as they say. But the problem is that you can go down an order of magnitude, but your power factor goes down because the mobility of the electrons go down. So you have now a trade-off. So the question is there room in between that you can manipulate the thermal conductivity without affecting S squared sigma? This has sort of intrigued us. We got together, we formed a group, we got a MURI funded from ONR, and then some DARPA funding. We sort of dug deeper. We had an idea, a concept. And the concept was borrowed from radiation. And the idea was the following, that if you look at the alloy limit, we don't really, people had not paid attention to the spectral side of phonon scattering, okay? But it is true, just like in photon radiation, these small atomic scale defects would scatter the short wavelength phonons much more efficiently than the long wavelength phonons, right? I mean, this is Rayleigh scattering. You got d raised to 6, lambda raised to 4. And this is what happens. Why you get the sky is blue, you get, molecular particles, molecules scattering the light, and blue is scattered much more efficiently. That's why you get blue sky. But these mid-wavelength phonons and the long wavelength phonons then contribute to heat conduction because they're not efficiently scattered. So we said, why don't we put some cloud in the sky now and put some scatterers which are on the order of the size of the wavelength. Okay. In fact, what you want is a whole broad size distribution of particles so that all the wavelengths are scattered, and so that you don't have propagation of heat, propagation of these waves. And so that was the idea. But of course, the size has to match up. So you asked, where's lambda max? And lambda max turns out to be a few nanometers. So okay, we may need some few nanometer particles in there. And so the concept was, if you embed these particles, is the thermal conductivity of this composite lower than that? And still be a crystalline material because the electrons still need to move. And that was the concept. So we got together. So Art Gossard is at Santa Barbara. He's one of the gurus of MBE growth of materials. Ali Shakuri, we got together. And my student, Wuchul Kim, Josh Zaid was Art's student, and some electron microscopist, Suzanne Stemmer and Klenov. And we looked at this material of indium gallium arsenide, and Art Gossard is the guru of 3-5 semiconductor MBE bandgap engineering. I mean, he's done it all. So indium gallium arsenide he could do, and then erbium arsenide is the other material which, if you do an MBE growth in this and just open the shutters, you don't have to do any layer by layer, open the shutters. These erbium arsenide will essentially self-assemble into nanoparticles, okay, on the order of a few nanometers, and epitaxially embed them in an indium gallium arsenide crystal. And so the question was, okay, this is great. If you do nothing, you get a sort of a fairly nice distribution of particles. Is the thermal conductivity of this material lower than that of indium gallium arsenide itself? Okay. And what we found was certainly that. This is indium gallium arsenide alloy. And if you put indium gallium arsenide at 0.3%, 3%, 6%, the thermal conductivity goes down by a factor of 3 or 4. Okay. And not only that, the electronic structure actually improves because erbium arsenide is metallic. And as we embed that in the indium gallium arsenide matrix, this actually dopes indium gallium arsenide then. And there is the mobility. If you go to about 3%, you're still okay. At 6%, the mobility goes down. But you can optimize that. And here is ZT of this material going up as a function of temperature. This is indium gallium arsenide itself. And you can cross 1, you can get 1.4 or so. But this was a model system. That is, it worked for this because we could control the material. And it happens to be a pretty good, semiconductor as well. There's some other bandgap engineering that was developed for this. But nevertheless, this is not a magic thing that you can suddenly get ZTO greater than 1 because you can actually design the material for it. So we started looking at that, and Gang Chen and Millie Dresselhaus also looked at that in the last couple of years. They said, instead of making this high MBE thing, why don't we just make nano stuff by ball milling, put them together, sinter this damn thing, and see what happens. And they did it not only for, what they found again was reduction of thermal conductivity without affecting the numerator, the power, the electronic side. And they did it for bismuth telluride, they did it for silicon germanium, and they showed that you can actually increase ZT greater than 1. And about 1.4 or so, just like we have done for indium gallium arsenide. This is silicon germanium, that is bismuth telluride, etc. So again, it was all phonon engineering. The question was, okay, we can get to about 1.5. Getting to 2 is difficult. Rama Venkata Subramanian showed 2.4. but that's really, really hard. Is there a fundamental jump that we can, is there something that we can do much more, that we can actually jump, can leapfrog over these incremental changes? These have become incremental right now. Last decade it was not incremental, now it is. The question is, can we jump even further? Which means you got to find new ways of reducing thermal conductivity that has not been tried before, okay? Or changing the power factor that has not been tried before. This has gotten us intriguing, and we took a very different approach, which is almost blasphemous. And that is using silicon. And silicon, as I said, is a light semiconductor. The thermal conductivity is very high. The people in the semiconductor industry like that because they can dissipate heat. And I'll show you the numbers. It doesn't make sense at all, except for a few other things that the physics can be controlled in very interesting ways. And let me explain. In silicon, or in semiconductors where the electronic mean free path is a few nanometers, and in doped silicon it is, and the phonon mean free path is several hundred nanometers, there is a length scale gap. Which means if you make your semiconductor this size, you will not change your electronic properties, but you will reduce your thermal conductivity by an order of magnitude. And that's the idea. So, this is silicon. The mean free path is anywhere from, depending on the wavelength of the phonons, anywhere from 100 to 1,000 nanometers. Bismuth telluride is 1 nanometer or so. The thermal conductivity as a result is 2 orders of magnitude higher because the mean free path is 2 orders of magnitude higher. In the power factor side, the numerator, the electronic side, silicon is actually a little bit better than bismuth telluride, but it's about the same number. And so this ZT is about 0.8, and this is 2 orders of magnitude lower, primarily because of thermal conductivity. Abundance, this is 48 parts per billion. Tellurium, 5 parts per billion. This is 27% of the Earth. So he said, okay, the thing is thermal conductivity out here. And so if we are thermal conductivity jocks about this, let's go after it and see if there's any chance of doing anything interesting out here to reduce the size and reduce the thermal conductivity by 2 orders of magnitude. And we don't understand all the principles, I can say it up front, but we are trying to see whether we can get down there. So the idea was to make nanowires, okay, and to reduce the size. And we developed this technique, most of you probably know this, if not, I'll go very quickly, of measuring the thermal conductivity of single individual nanowires. These are 2 suspended, this is a classic heat conduction experiment. 2 heaters, 2 temperature reservoirs, one higher temperature, lower temperature. You pass current through this, you electrically heat this, and you can get I-squared behavior of this for current and temperature. And there's a 4-point probe, so you can use it as a heater and a temperature sensor. You heat this, the heat flows on through this nanowire to the other side, raises its temperature. You pass a small AC current to measure the temperature of this, and the temperature you can measure. And this temperature difference, and also by characterizing these legs, you can find the conductance of these legs. You can actually get the total heat flow through this, the temperature difference, and you can get the conductance. And from the geometry and the conductance, you can get the thermal conductivity, you can do everything you want. And we have used this for carbon nanotubes. Whatever one-dimensional nanostructure we can find, we can put it on it and see what the thermal conductivity is. So we said, okay, let's look at, these are some early experiments of a new way of, actually not so new. There were some experiments in the 70s, but nevertheless, a very interesting way of making single crystal silicon nanowires. This is single crystal by putting sort of a catalyst of gold on a surface and then exposing silicon. It forms a silicon gold alloy, and after beyond a certain point, silicon is precipitated out, which forms a nanowire of the size of this particle. And then the question is, can we break off some of these nanowires, put it on our device and measure? And the idea is that we can control the diameter of this by controlling the size. And if this diameter is smaller than the mean free path, then these phonons would bounce off the boundaries, and instead of the mean free path be controlled by phonon-phonon scattering, the diameter would control the mean free path, and you get 1/3 CVD. So as your D goes down, your thermal conductivity goes down. This is a fairly well-known approach. The question, does it work? It certainly does work. This is thermal conductivity as a function of temperature for different sizes, 115 nanometers, 56, 37, 22. Even this is on the order of 50, whereas bulk semiconductor silicon is 140. So this, you can say right away that the mean free path is certainly, in the bulk, is certainly larger than 115 nanometer. And in fact, on the order of 300, 400 nanometers, some of them about a micron. As you get down to 22, the theory, this is Boltzmann transport, does not match up. Some very interesting physics comes out of that itself. Nevertheless, you can control. But even in this, you're at room temperature, which is our interest, is at about 5 watts per meter Kelvin. That's just not good enough. So serendipitously, my colleague here, Peidong Yang, was developing these other nanowires for photonic application for photovoltaics by making, the pictures have not come out right, by taking a silicon wafer, instead of growing the nanowires, actually etching it. And using the electrochemical etching process, electroless etching process, you get roughened nanowires. And these are still single crystal. This is VLS, very smooth surfaces. This is the roughened wires where there's jagged surfaces. And we said, let's just put it out there and see what happens. And what we found, these were this is 115, 56, 37 of the previous data. This is electroless etched wires, which are, this is 115, 98, 60, 50, about a factor of 4 to 5 or 6 lower thermal conductivity by the roughness. And we thought this can be true. So we repeated the experiments, it reduced the contact resistance by various different ways, and we found similar results, but uncontrolled. We could not control the thermal conductivity, but it was low. So what we also found in some of the wires, this is thermal conductivity as a function of temperature, some of the wires, depending on the doping level and the roughness, it approached the amorphous limit in a crystalline wire, which was totally, mind-boggling for us because we never expected that. And one would not expect that. So, and as a result, the ZT shot up to about 0.6 or so, and that turned out to be quite interesting because now we're within the range of hitting the target of 1 and beyond. The question is, why does the thermal conductivity go down, and is this really true? Does the roughness really control the thermal conductivity? And we did many other experiments. So the questions are, why does surface roughness decrease K? Why does K approach the amorphous limit in crystalline material? Simple Boltzmann theory does not explain the results out here. And this is thermal conductivity as a function of etching time, which controls roughness. So these are the TM pictures. This is smooth, slightly rough. So we went from the VLS wire, which was really smooth, and started etching those instead of making just etched wires. And as you increase the roughness, yes, the thermal conductivity goes down. And that's, again, Boltzmann transport doesn't quite explain. Question is why? And I would say we still don't understand completely. But one of the things that we are looking at is that if, again, going back to the spectral side, is something that, again, we're trying to prove this. We don't know whether it's true or not, but it's a hunch. And the hunch is maybe there's some correlated effect of multiple scattering events that are happening. These are elastic scattering. And the idea is that if you bring in disorder in a system, these waves will interfere in ways that are that have been looked at for electronic systems and photons. And there's a famous paper by Phil Anderson in 1958 called Anderson Localization. And Anderson Localization says that if you get a metal, for example, and the metal is conducting, if you increase the degree of disorder in the metal, this electronic wave function will scatter, but they will scatter in such a way that locally they will interfere destructively. And essentially the wave packet will not propagate. You will localize it, and you'll get evanescent waves then later on. And thereby you can make the metal to be an insulator. So this transition, and of course there are other theories, Mott insulators, etc., that came around. And it is a very famous, not all of localization have been explained in different dimensions, but this is very well known in the electronic field. And there is no reason, so people have shown it for electrons. In the early 90s, people actually showed it for photons. And there's no reason why it should not work for any wave, as long as there's sufficient amount of disorder in this. So we said that maybe this is happening. I don't know whether it's happening or not. It's worth a shot. And in this will only happen when the wave does not dephase. That means you need a material which is crystalline, and you need the mean free paths, the coherence lengths, to be long, because that's how you get destructive interference. So it'd rather happen in silicon and diamond than in bismuth telluride, which is a completely different way of looking at things. So we did some theory, and this is my colleague in physics department, Berkeley, Joel Moore, and his students, Patrick Murphy. They said, okay, what is the length scale involved? What are the different length scales involved in this? One is the dephasing length. Dephasing length is the following, that if you have phonon-phonon scattering, you lose all memory of the phase. And if you lose memory of the phase, these correlated scattering events are gone. There will be no correlated scattering. So the length scale of your object that you're looking at has to be lower than the dephasing length. And so that is one length scale, length of the nanowire. The other is the localization length. That means it needs time for it to interfere, for it to localize. And there's a length scale associated with that. Well, the size of the object better be larger than the localization length, otherwise the evanescent waves will grab the energy and just move along. So that's the length scale. So we said that let's at least figure out, as a function of the roughness of these wires, the size, and in this case, the autocorrelation length, what is the dephasing length and what is the localization length? And it turns out, I mean, we were hoping it would go to the room temperature. But right now, at least the theory predicts that it's most likely going to happen in this lower temperature. And no one yet, to my knowledge, or to the knowledge of all the physicists that have worked in it in the 60s and 70s, has ever shown localization phenomena, Anderson localization for phonons yet. If you could localize, then you can really reduce the phonon conductance by interference effects, which is totally wave spectral, which can reduce the thermal conductivity even below the amorphous limit. And that's what we're going after. So what are the signatures of localization? Well, if you plot the thermal conductivity, or conductance times length, which is really the thermal conductivity, if it's purely diffusion, it would have no length dependence. If it is ballistic transport, the thermal conductivity increases as a function of length because conductance is constant. But if it is localization, the thermal conductivity will decrease with localization. And there is, if you find a sample or in a collection of samples with thermal conductivity of the material decreases with length, increasing length, I don't know of any other reason but localization. But no one has ever observed this. The other effect is the temperature dependence. And the temperature dependence, this is conductance versus temperature. If it's purely classical heat conduction, or classical in the sense you have T-cube behavior for the heat capacity and propagation of all the modes, you will see something like this. You'll see a little bit of linear, and then increasing as the more and more modes get excited, you will get this increasing thing out here. If you have localization, you will see a region which is flat, where you can excite the modes, but they won't propagate. And this essentially flatten out. And at least my theoretical colleagues predict it's going to be lower than the quantum of thermal conductance. Just like you have quantum of electrical conductance, the quantum is this, pi squared kb squared over 3h multiplied by t. It's linear with t. And this quantum has been shown. There was a beautiful experiment done at Caltech by Rukas and Schwab, etc., where they showed this quantum of phonon conductance, which is independent of all material parameters, only depends on the physical constants down in the millikelvin temperature. If this is true, then only the fundamental modes should travel, and you'll be able to see at much higher temperatures as well. So this is the experiment that we are trying in my lab right now, is to see whether we can get these length and temperature dependence. So instead of making these nanowires separately, we said that, this issue about contact resistance is a big deal. We need to control the size, dimension, and everything. And putting wires on a device is not the way to go. So we changed our whole experimental system. And we are now making electron beam lithography wires integrated in the silicon nanowires are integrated together. They're made of the same material as the heater. Okay, so this is using silicon and insulator device, wafers, making the pattern. Everything is integrated. And when you do e-beam lithography and photolithography, you can control the length, you can control the dimension, you control everything. And since it is monolithic, there is no contact resistance. And so that's the way to go if you really want to get into the science and understand this in the right way. So these are now devices. These are 60 nanometers by 40 nanometers. You don't see them very well out here. You can make ribbons, of course. You can make 100 nanometers, 40 nanometers, but long, you can control the length because everything is lithography now. There is no nanowire being put. And, so these are the devices that we are now trying. This fabrication turned out to be really hard for a variety of reasons. We are now getting the devices and we are trying them out. These are single crystal. These are roughened. Also, the roughness is not controlled, but nevertheless there's roughness. And we have measured the thermal resistance as a function of length. And the good news is that as you reduce the length, it goes to zero, the resistance, which means there is no contact resistance, which is a good thing. Because people have been asking us questions about our previous data. They said, well, there is no contact resistance out here. This is data showing that. And we have now measured the first few measurements of thermal conductivity as a function of temperature of these VLS wires that I showed you. This is the electron beam lithography, slightly roughened. These are the really roughened wires of EE. And we're seeing at least in the order of magnitude. Have we seen localization yet? Not yet, but stay tuned. This is the experiment that we're trying, and we'll see how it goes. The only data will show us. So anyway, let me summarize. I very briefly talked about limits of boiling, thermodynamic limits of air conditioning, but I spent some time in getting deep into one subject which we are now pursuing is beating limits of thermal conduction, beating the alloy limit, approaching the amorphous limit, and hopefully beating the amorphous limit using localization, which would be new. I don't think people have really tried that, pushed hard on that. Although people were pushing that in the 70s. Venke, Horst Stomer, and others were trying to do that. Anyway, let me stop out here. Let me thank all the sponsors of this and all my collaborators in Berkeley, Santa Barbara, Tim Sands out here, and many others. Let me stop. Thank you very much. Yeah.
I have a question about the phonon localization. So I think the phonon localization has to do with some kind of geometry parameters, like the roughness scale, the length scale, something like that. But the phonon, on the other hand, had a broad range of wavelengths.
Right.
And say maybe a certain length scale will localize a certain phonons with a certain wavelengths, but
This is a good question, because phonon broad spectrum, how do you localize all of them? If you get the roughness, okay, if you look at a roughness and look at the spectrum of that, look at that in K-space, you will find that it's a broad spectrum as well. So random is good in this. Periodicity is bad. So, if you make a superlattice structure the same period, you get one length scale in, but the other phonons go through. So some phonons are localized then, which is the famous experiment with Venke, Horst Stomer, and Bob Dines of making band gaps in gallium arsenide, aluminum gallium arsenide in the 70s, where they were able to localize one band. But if you make it random, you get essentially resonant coupling between the K vector of the phonons and the K vector of the roughness. And then you can do it. So randomness over a whole range of length scales is a good thing out here. But you cannot localize the fundamental modes. The fundamental modes of acoustic, the torsional mode, the two transverse modes, and the longitudinal mode cannot be localized by roughness. So for that, then it's a wave scattering problem. You can put impedances in between. You can turn the wire around. You can do all kinds of things, but reflect those what?
Directions, and the probability of along a certain direction probably is small. And
that's right. Right. Yep.
So going back to the fact that even when the wires are monolithic, and you say that contact resistance better be zero, if we go back to basic, phonon transmission through apertures, aren't these wires already small enough that
yeah, so there's a
contribute to enough?
Right. There's a Bethe scattering limit of size raised to 6, right, for any wave propagation through an aperture. These apertures are 40 nanometers now. It's not small enough. You have to get down to a few nanometers for those wires, which are really hard to make. So we're not at that limit yet. Yeah. Yep.
I've seen some recent data on twin crystal structures where there's a edge, a disorder in the edges. Do you think that maybe that's an experiment? Have you thought about looking at those, or could that help with the question?
That could help, because there'll be an impedance of that. Potentially that could help. Right now we're just trying to make our devices and get some data and see, but there are a lot of experiments I want to do. By changing impedances on board this device, you could actually get to, these are so-called one-dimensional. These are not really one-dimensional. They're, for all practical purposes, they're 3D. But you could get to 1D structures and look at phonon transport in 1D structures. There are a lot of experiments that can be done, including the twins, but we haven't had the bandwidth yet. But if anyone wants to do it, I'll be happy to tell you how we do it. Yeah.
When ARC is growing those, indium gallium aluminum arsenide alloys, are you adjusting the composition so that you get a small separation between the central valley and the satellite valley? You get a big asymmetry in your
right. Yeah, so I didn't talk about the electronic side of it. There is actually this is where John Bowers, Ali Shakuri, Art Gossett come in. Art Gossett grows the materials where they take, it's actually digital alloying for indium gallium arsenide and indium gallium aluminum arsenide to control the band edge. The band edge has to be controlled to few kTs.
There's two bands, so you got central
right, right.
You get a big change in the density states
right.
at a certain point, which would give you that asymmetry you're looking for.
That's right. And so they are doing that. Both the band offset as well as the band control of the single band of the different valleys. But there's also more to it. There's, there's electron momentum conservation. So if you have a flat interface, you actually, you only have, like Snell's law, you only have a few electrons which will go through. Others will be totally internally reflected. So they actually put some very interesting roughness on this to get other electrons to go through. So increase the transmission, just like in optics. And thereby they have been able to increase the electron conductivity through that without affecting the thermal power. And that, there's some very nifty bandgap engineering and structural engineering that have gone into these structures on the electronic side. Yeah. Yep.
So based on your experience, like thermoelectricity, so especially based on power factor, so is it superlattice or bulk? What is the way to go in future?
I don't see any reason to go in superlattice, really, frankly, because, well, I shouldn't say that. People expected that when you go to a superlattice, you'll get band gaps and everything. It hasn't really been true. No one has really seen band gaps except for a very few experiments, and no one quite understands, because even if you have a sharp interface, it's not quite sharp, there's roughness out there, so coherence is lost. So the thermal conductivity is basically a function of interface density. That's it. There is no coherent effect. So if you can make interfaces very, close, yeah, maybe that's the way to go. But at the end of the day, you have to reduce the thermal conductivity below 1. That's the key, 1 watt per meter Kelvin. On the other hand, random surfaces are much easier to grow. Or random materials are much easier to grow. And there's a practical aspect of it, the engineering side of it, of how to make these materials and use them. I mean, Gangchen's approach of ball milling, Gangchen and Zifeng Ren and all, ball milling and making a bulk material out of nanostructure, that's great. I think that's the way to go. Yeah.
But in the same context, but the Gangchen material is amorphous, so why it's electronic conductivity?
It's not amorphous. It's nanocrystalline. So there are grains which are nanosize, and But I know that it's not. I know that this is Tim Sands. We are part of the same program. I think you guys are looking at scandium nitride and gallium nitride or zirconium nitride, right? I won't say super lattice structure, it's a multi-layer structure. I don't think the crystalline, that is showing some very interesting results. And there is a electronic contribution to thermal conductivity, I believe, that we cannot quite explain right now. We are measuring the thermal conductivity of your samples out here. I don't know who's growing them, but it's not quite explained totally yet. But very interesting. The power factor seems really good. So, Jyoti?
Then if we taken a shot at actually doing scattering computations theoretically to pick up this localization set, looking at wire.
Very few. There's one molecular dynamics that came out of UC Davis, Julia Gali. He did that only recently. It was a Nanolators paper. But this has been known for a while. When I talked to Venki and all that, they were trying this. They were just not successful in doing this. They knew there was, Anderson localization was not new in the 1970s, right? 1958.
Well, that's not the big question, right? It's accepted that it exists.
It exists, but no one knows whether it actually happens or not. It should exist. It's not exist. It should exist, but no one has demonstrated because unlike electrons and photons, phonons have this, phonon-phonon scattering effect, right? So if you try to localize one mode, you get it leaked through other modes. So no one has been able to, as you were asking, no one has been able to localize all the modes. And that's what we're trying out here, because if you make it random roughness, as I said, the spectrum has to be broad enough and match the spectrum of the phonons. Then you get resonant coupling. That has not been done. And I don't think anyone has actually seen it, because it is not, it's very hard to approach this through molecular dynamics, because I don't think you'll capture the length scales. Okay? It has to be a wave mechanics problem. Absolutely, yeah. But you have a chance of doing it if you get away from MD. Right?
Let's thank Dr. Majumdar again for one.
Thanks. I'm done with my talks, right?